In 7.1, that's where we just talked about linear correlations and nonlinear correlations and no correlation. We talked about what the scatter plots look like, what the R value meant, and what we might expect for certain pairs of variables. But we didn't do any predictions, and that's really one good thing that we use the linear regression equation for. In college algebra, not just college algebra, heck, in 8th grade or 9th grade, we started given 2 points. You can find the equation of the line, right? Theoretically, you may have forgotten exactly how to do that, but if I give you 2 points and reminded you the process, you could find the equation of the line. Once you have the equation of the line, it's useful for predicting other things. For example, if you had an equation that models the demand of a certain item given its price, then I could ask you questions like, what if it costs $3? What if it costs $3.50? What if it costs $2.75? And you just plug those values into the equations and you get the prediction. Well, like I mentioned last week, statistics is doing pretty much the same thing, but rather than just having 2 points to find the equation of the line, we might have 100 points. And we're not going to find, in most cases, one line or one equation that all 100 points lie perfectly on, but we can find a best fit line, a line that fits the data better than others. And then sometimes we can use it to make predictions. We have to know when we can use it to make predictions and what we can use if we can't use that best fit line. So, assessing linear correlation using critical values. Last week we said, how do you know when R is close enough? Is R equals 0.7 good enough to make a prediction? We got to have some way to quantify what's good enough to say, yes, we can use this equation to make predictions. So what we're going to use is a table of critical values. This table A5 we'll get to in just a minute. This table shows the cost of a slice of pizza and the cost of subway fare in a sample of 6 years between 1960 and 2003. Would you expect there to be a linear relation between the cost of a slice of pizza and subway fare? Not unless the pizzas were being delivered on the subway, and when the subway fare went up, the pizza cost has to go up. No, I think they're probably not related. We can use the TI-84 to make a scatter plot, which we did last week. And remember, linear regression t-test, lin-reg test, is what we use to find the R value. And it turns out that R value is very strong. R equals 0.988. For these 6 years, there was a very strong linear relationship between the cost of a slice of pizza and subway fare. Now, does that mean that as the cost of pizza goes up, that's causing the cost of subway fare to go up? No. What's our most favorite word, or our most favorite sentence in statistics?
Correlation isn't.
Yeah, correlation does not imply causation. Just because there is a relationship between two things doesn't mean one is causing the other. There appears to be a strong correlation, but how do we know whether an R value is close enough to either +1 or -1 to support that claim that there is a linear relationship? Well, to have a definitive way, good morning, we will use this table of critical values. Statisticians came up with these critical values a long time ago, and they are based on sample size. So I gave you the critical values for sample sizes from 4 to 16. Any problems I give you will have between 4 and 16 data points, so you'll be able to use this table on it. That alpha equals 0.05 is called your significance level. That is how certain you need to be. When we do hypothesis test in chapter 9, we're going to say the more consequential the results of your data or the decision that you make based on your data, the more consequential the decision is, the stronger significance level you have to have, or the more confident you have to be in your decision. If it's a life and death thing, you might want to use 99% as your confidence level. But if it's just a matter of, no, I need to make this decision, but nobody's going to live or die, then maybe a 90% confidence level is enough. But for this table, we're only going to be using 95% confidence level, which is a 0.05 significance level. The critical values are based on sample size and significance level. The lower the sample size, the higher the critical value, because it's more difficult to be certain of a linear relationship in small samples than in large samples. If you have 100 data points, you're going to be able to look at that scatter plot and go, yeah, there looks like there's a pretty strong linear relation, or no, it doesn't. But if you have just a sample size of 5, it's harder to say with certainty whether or not there is a linear correlation. So the smaller the sample size, the larger critical value you have to have. I'll give you that table on the test. I'm trying to think if it's on every homework problem. If it's not in every homework problem, don't forget you have this table in your notes. You might have to look at it in your notes if it's not on one of the homework problems. Also, only positive critical values are given, but for each positive critical value, there's a negative critical value as well. So there are problems in the homework that say give the critical values plural or a sample size of 10. If it says plural, then not only will you give the positive 0.632, but negative 0.632 as well. Blah, 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 blah. To determine whether an R value is strong enough, we plot the critical values on a number line for a sample size of 6 years here. The R value would be this 0.811. So if we plot negative 0.811 and positive 0.811 and our R value all on a number line, you can see that the positive R value, or the R value 0.988, is out past the positive critical value. In close to 0, this would mean when R equals 0, we have no correlation, or at least not a linear correlation. But out here and out here, past the critical values to the right or past the critical value to the left, that means there is a linear correlation. And that word linear is important. I don't always say it, but there are other types of correlations, so I need to be specific. So now we're not just going to look at a scatter plot and say, it looks like a strong correlation to me. Or we're not going to look at just an R value and say, it looks like a strong linear correlation to me. We're going to get the critical values from the table, put the positive critical value and the negative critical value on a number line, and then our R value, which for this was 0.988, we're going to plot that, and we're going to say in close to 0 means no correlation. Out past the critical numbers means there is a linear correlation. And that's how we're going to decide whether or not to say, yes, there is a linear correlation. And that's what this picture right here shows. Whatever the critical values are, out past the critical value to the right or to the left, that means far away from 0. 0 means no linear correlation. Far away from 0 means there is a linear correlation. So if we determine that there is a linear correlation, what can we do with that? Well, if there is a linear equation, we should be able to find the equation of the line. We do that in algebra. You give me 2 points, I find the equation of the line. It's a lot harder to do manually if you have 10, 20, 50, 100 points, but there's a button for it on the TI 84. Actually, it's the same button that gives you your R value. It's LinReg t-test, gives you the values that you need to plug into the equation of the line. Now, speaking of equation of the line, what's that y equals mx plus b form? What's that called? Anybody remember? What's that m stand for? Slope. And the b is the y-intercept. That's called slope-intercept form in algebra. Well, our calculator is going to give us the m and the b, the slope and the y-intercept, and we're just going to plug it into slope-intercept form. We don't have to have a formula for finding m like we do in algebra. If I plug that subway data, well, let me back up a second. The line, if you draw it, is called the regression line, and the equation that gives you that line is called the regression equation. If we can find the regression equation for a set of data, then maybe we can use it to make predictions. All right. Pull up LinReg t-test. You know what? Not unless we're going to need it for something else. We're not going to need it for something else. I don't want you to take time to put in those Subway and pizza fares. And I took a screenshot of when I had done that already. This LinReg t-test, remember R doesn't show up on the first screen. You have to scroll down a little bit to get your R value. But if we determine that there is a linear correlation, then in addition to that R value, we're going to use this A and this B, where A is the y-intercept and B is the slope. And we're going to plug those values in the general equation, y equals a plus bx. That could also be written as bx plus a or mx plus b. It's all different letters for the same thing. The coefficient of x is always your slope. And your a is always your y-intercept. And that's what the next couple paragraphs are about. The value of A is the y-intercept. The y-intercept is, in algebra, it's where the line crosses the y-axis. What do you know about all the x's on the y-axis? If a point is on the y-axis, what's its x?
0.
Because you haven't gone left or right. So the y-intercept is always what you would get if you let x be 0. And in this case, x is your cost of a slice of pizza. So if pizza were 0, then the y-intercept would be the cost of a slice, would be the cost of the subway fare when pizza is $0 per slice. And then the slope tells you how much the y values change for each unit change in x. What do we know about lines with a positive slope? What do they look like? They go uphill from left to right, and lines with negative slope go oh, I did the wrong thing. Mirror image, up from left to right. Negative slope goes down from left to right. And so that same thing would be true about these values of B. A positive slope, like a positive R value, indicates as X gets larger, Y gets larger. A negative slope, like a negative R value, means as X gets larger, Y gets smaller. So for our pizza Subway data, the slope being about 0.945, that's the coefficient of X, that's your B, just round it to 0.95. That means for each dollar that pizza goes up, Subway fare goes up about 95 cents. That's what that slope means. Notice at the top of the equation, the regression equation is given in the form A plus BX. In statistics, we usually use Y hat. That's really how you pronounce it. This is Y hat. Is the estimated value of Y when we use the regression equation to make predictions. So we write our equation, instead of writing it Y equals A plus BX, we can write it Y hat equal A plus BX. Or sometimes in the homework, in parentheses, they'll have write your answer in the form Y hat equals BX plus A. It really doesn't matter which is written first, your y-intercept or your term with the slope. So you could either write Y hat equals BX plus A or Y hat equals A plus BX. In both cases, B is your slope and A is your y-intercept. Regardless of the order of those terms, the number in front of X is always the slope, and the constant is always the y-intercept. So for our pizza Subway fare data, we could write the equation either way, but Y hat is the symbol that we're going to use for the regression equation. If we graph that line right on top of our scatter plot, we see that it hits pretty darn dead on 1, 2, 3 of the points, and then 3 of the points are a little bit off, but still very close to that line. That's why it's called the best fit line, or the equation's called the best fit equation. All of this since 7.1 has been leading up to us being able to make predictions. That's what we use the equation of a line for in algebra, and it's what we use the equation of the regression line for in statistics. Calculator will always give me that A and B. If I enter some data in list 1 and list 2 and run linear regression t-test, the calculator will always give me an A and a B. I can always write a regression equation. But just because I can write one, does that mean I should use it to make predictions? Well, not if there's not a linear correlation. Just because the equation gives me, or because the calculator gives me that equation, doesn't mean I can use it. I still have to verify that there is a linear correlation. I still have to put that R value on the number line with critical numbers and say, in the middle there is no correlation. On the ends there is a correlation. I have to verify that before I can use my equation to make predictions. because we did verify that there was a linear correlation between the cost of pizza and the cost of Subway fare. If you said, predict the cost of Subway fare when a slice of pizza is $1.50, you just put 1.5 in for X and you get about 1.45. So when pizza is $1.50, Subway fare is approximately $1.45, according to this model. And we only can do that because we've already verified that R equals 0.988 did indicate a linear correlation. It's vital to understand that you can only use the regression equation once a linear relationship has been confirmed. Don't automatically go plugging stuff into that equation every time you're asked to make a prediction. If the linear correlation cannot be confirmed and you still insist on having a prediction, the best that you can do when there's not a linear correlation is just the mean of the Y values. And it's usually not a very good predictor. It's just the best thing we have when there is no linear correlation. All right, I like flowcharts. This flowchart helps me decide whether to use the regression equation or the mean of the sample Y's. Here are the questions you have to ask yourself. Is the linear regression equation a good model? Well, you can look at the scatter plot and go, yeah, it looks like a linear relation. You mainly want to go by this R value. That's not going to show up yellow on yellow, but does R indicate that there's a linear correlation? And remember, that's going to be, is R outside the critical values? And then the third question is what you're asking me to make a prediction for within the scope of the other data? We could come up with an equation, a growth equation for children their first 12 months. Should you use that same equation to predict how tall a person's going to be when they're an adult? Do people keep growing the same rate their first 21 years as they did their first year? Would all be giants? No. You can't use an equation that's based on one set of data to make a prediction that's way outside that set of data. And that's what's meant by not much beyond the scope of the available data. So if we answer yes to all three of these things, then we can use the regression equation to make a prediction. But if not, don't use the regression equation. If it's not a good, strong linear correlation, then don't use the regression equation to make predictions. And when we can't use the regression equation to make predictions, what are we going to use? Ms. Apple, what are we going to use when we cannot use the regression equation? The mean of the Y values. So we're always going to be using one of those two things, either the regression equation or the mean of the Y values. We just need to verify that there is a linear relation before we use the regression equation. All right, important notes, and then we will look at some examples. The second condition, R indicates that there's a linear correlation. That means when you put the R value on a number line with the positive and negative critical values, R is in one of the regions outside the critical numbers. That's what we wrote right here. The third condition means that the value of the explanatory variable, remember that's your X, doesn't differ much from the other X values in the given data. Don't use the baby's 0 through 12-month equation to predict how tall they're going to be when they're 18. Predicting Y values with X values that are far away from the given data is called extrapolation and could result in bad predictions. Our pizza Subway data was only from approximately 1960 to 2003. Whatever equation we come up with, I wouldn't use that equation to predict the cost of Subway fare in 2026. That's 26 years after this data was gathered. So you wouldn't use it. And then the third thing is if any one of these three conditions is not met, then the best predicted Y value for any X is the mean of the sample Ys. If your Ys are saved in list 2, then you can find the mean of the Ys. You could use one variable stats, since we're already familiar with that. Just make sure that you pick the mean, that you enter list 2 instead of list 1. You want the mean of the Ys, not the mean of the X's. This is a different way to get the mean of the Ys. And I'm going to say for one var stats for list 2 would also work. All right. Hardest thing about tonight's homework is just remembering to not automatically use the regression equation. Your calculator will give you the regression equation every time, but it's up to you to decide whether or not you should use it. Example 1. Listed below are the number of commuters and the number of parking spots at a sample of 8 rail stations in Connecticut. Does it seem like there would be a relationship, a linear relationship between the number of commuters and number of parking spots? Seems like there should be. The more commuters you have, the more parking spots you're going to need to have. So there should be a linear correlation. That's my gut impulse. The Metro North Station of Greenwich, Connecticut has 2,804 commuters. Find the best predicted number of parking spots at that station, and then compare it to the actual number of parking spots we know to be 1,274. So go ahead and do this. Put all of your number of commuters in list 1 and put your number of parking spots in list 2. Always double check your data. You do not want to miss a test question because you've made a typo. And I have one typo. That last X was 2532. All right. Second, quit to get out of that. Do you remember how to make the stat plot? If I already have it set up, which we last week learned how to set up the stat plot, how do I get it to actually draw the scatter plot? I believe it was under Zoom. Number 9 says Zoom stat. Zoom and 9 gives me that scatter plot, which I've copied in your notes, so you have that. Is it showing all 8 data points? Is anybody not getting that scatter plot and need some help? All right. Does it look like there's a linear relationship between number of commuters and number of parking spots? Just looking at the scatter plot. Yeah, it does. That's the first thing I need to check. Then I need to find my value of R. Where do I find that?
Like list P or it's the T something or
Let's see.
Right.
Stat. This is from 7.1 notes. Stat, and then tests. And scroll all the way down to, I believe it's F. It says Lin Reg T-test. That's linear regression T-test. And enter. Tell the calculator, yes, I want to pick my X's from list 1, my Y's from list 2. They each have a frequency of 1. And remember, for the linear regression T-test, you're always going to say not equal to 0. And then go down to calculate. And I have, I think I have the screenshot of that in, yeah, the screenshot of that in your notes as well. Now, I don't see my R value on this first screen, but I think if I scroll down once, I see R squared, and then again, I see R. R is about 0.901. So my value of R is 0.901. Now, where am I going to get those critical values? Miss Lily, where are you looking? You flipped backwards in your notes, and I was going to go, yeah, that's right. Where do you get those critical values for R? Let me highlight that in case you need it for your homework.
Do you use one table for every problem?
Yes. Critical values are only based on the sample size and the confidence level or significance level. I could add other rows for other significance levels, like the significance level was 0.01 or 0.1. but all of our homework problems just say significance level 0.05, so I only gave you that row. All right, so how many data points did we have for that set of data we're working on? 8. So for a sample size of 8 and a significance level of 0.05, what's our critical number? 0.707 from the table. And then if you ask me plural, then there's also a negative 0.707. So how am I going to decide? Let me write that here. R is plus or minus 0.707. That R value and these critical numbers to determine if there is a linear relationship. Your hands are doing all the right things, Sarah. You plot. The word is plot. Yes.
If your is side of the things.
That's exactly right. Because halfway between negative 0.0 or 0.707 and positive 0.707, what's halfway between them? 0. And what does 0 mean when you're talking about linear correlation? No correlation in the middle, but our 0.901 is out here, out past the critical value. So yes, our R value does indicate that there is a linear correlation, which our scatter plot told us, I think so, and our gut instinct about these two variables told us, I think so, but now we have a definitive way of saying, yes, that's a strong enough R value to say that there is a linear relationship between number of commuters and number of parking spots. So now we're asked to make a prediction. What are we asked to predict? Best predicted number of parking spots when there are 2,804 commuters. That's the prediction they're asking us to make. Is 2,804 within the scope of these other X values? Well, our lowest X value is 277, and our highest is 3,453. 28,404 lies in that range. Or it'd be okay if it was a little bit outside that range. Maybe 3,500 would still be okay, but you wouldn't use it for, let's say, 10,000 commuters, because that's far outside the other X values that we have. So is the prediction within the scope of the available data? Yes. And so what's the equation of the regression line? What symbol do we use for the regression line? Y hat, good old Y hat.
Your A plus BX.
Yep, I always look up here to make sure my calculator is giving me this in the form A plus BX, where it gives me the A and the B. And I think always in MyLab, it'll tell you what to round to. Let's say it says round A to 1 decimal place. What would A be to 1 decimal place? 89.5. And then what if it said round this B to 3 decimal places? 0.409x. Which one of those numbers is my slope? So if this problem asks, what is the slope of the regression line, you'd say 0.409. If it said, what is the y-intercept, you'd say 89.5. What if it said, what does the y-intercept mean? What is that 89.5 telling us? It's the y-intercept. That means it's on the which axis?
Right.
It's on the y-axis, and if it's on the y-axis, then what's true about the ordered pair? All the points on the y-axis. You haven't gone left or right, so x is 0. So the y-intercept would be the parking spots for 0 commuters. Now, if there were 0 commuters, then they really wouldn't even need a parking place. But that's what the y-intercept would mean. That's what y is if x is 0. And then the slope gives you how many additional parking places you need for each commuter. For every commuter there is, we need about a half a parking place. I guess this is assuming some carpooling. You wouldn't need a spot for everybody. You just need a spot for every car. To graph the regression line with the scatter plot, you can enter the y equals on your calculator, y equals right there, and type that equation in. 89.5 plus 0.409. And your X is the key right beside your alpha button, the green alpha button. Look up and see if your equation looks like mine. 89.5 plus 409x. Now if I say graph, I get not only my scatter plot, but my regression line also. And yes, it looks like a pretty good fit. About 3 of the points are on the line, about 5 of the points are off the line, but really close to the line. It's the line of best fit. Now, we'll have to remember to go back and clear that y equals when we get to the next example. We don't want this line showing up on the next scatter plot, so I'm going to go ahead and do that now. Clear that just to be ready for next time. But did our regression line look like or fit the scatter plot well? Yeah, it did. The calculator gave us a regression equation and then asked me to find the value of the regression equation for x equals the prediction value, 2,804. So y hat would be 89.5 plus 0.409 times 2,804. Round that to the nearest whole parking spot for me. We're not going to have half spots. You have it, Jason?
1236.
1236. Does anybody second that? Anybody get anything different? All right. So according to this model, the Metro North Station of Greenwich, Connecticut, which has 2,804 commuters, according to the regression equation, it should have 1,236 parking spots. Now, the question is, do we trust that? Should we use the regression equation to predict the number of parking space at Metro North Station? Yeah, because we've already answered here. And yes, there, and yes, there, and yes, there. Those three yeses are the things that were in our flow chart here. If we answer yes to all of those, then yes, we can use the regression equation. So, yes. So our prediction is for 2,804 commuters, we should have 1,236 parking spots. Is that pretty close to the actual number of parking spots at the Metro North Station? Yeah. Maybe this is used by city planning or transit planning to see which rail stations or to prioritize the rail stations, which ones need more parking spots, because that's where we'll grow our money the first or next year, the one that is farthest away from the predicted value. All right, that was an example where there was a strong linear relationship between our variables, so we used the regression equation to make a prediction. The next one is the price in dollars and quality rating scores of rear projection televisions. I don't even know what a rear projection television is, but this is data from Consumer Reports, the price of these televisions and their quality score from Consumer Reports. Now, would you expect there to be a linear relationship? The more you pay, the better TV you get? Maybe, hopefully. Is that always true with electronics? No, that's certainly not always true. So let's find out for rear projection televisions if price seems to affect score in a linear manner. Go ahead and put all these prices in list 1 and all these scores in list 2. And then we'll look at it. I did. Since all right, and double check everything. Problem has two parts. Part one is there sufficient evidence to conclude that there is a linear correlation between price and the quality rating score of rear projection televisions? Do the results suggest that the more you pay, the better quality you get? All right, number one, does the scatter plot appear to have a linear relationship? Where do I find that? Zoom and then 9. Would you say the scatter plot makes you think there's a linear relationship?
I mean, there's those 3 points that look, but like the rest of them are too far.
Yeah. I'd say you could find a line that fit the first 5 points pretty well, but then at a certain point, the score stops going up and actually starts going down. So my gut, and this is all I'm saying, is just my gut says, no, there doesn't seem to be. But we don't know definitively until we compare R to the critical values. So where do I find my R value?
Test.
Okay, under tests, and either scroll down. Yeah, I always scroll down because I don't want to look for my F. It should already be all set up for me. So all I have to do is go down to calculate and then scroll down far enough to see R. To 3 decimal places, it's 0.543. And it seems like 3 decimal places would be a good number to round to, because all of my critical values on table A5 are to 3 decimal places. All right, looking back to that table, how many TVs were in our sample? 8 again. So it's going to have the same critical value as before, plus or minus 0.707. R, how do I determine the answer to this next question? Does R indicate there's a linear correlation between the variables? All right. How do I'm trying to beam you what I want you to say, and it's not going. How do you decide if it's close enough to -1 and 1 or 1? And comparing it to the critical values. So we put those critical values on a number line. This is what I was trying to get you to say, Lily. Yes. Correct. Exactly. It's closer to 0 than it is to being outside the critical numbers. my 0.543 here. Inside means no. So do those data points seem to suggest that the more you pay, the better quality you get? No. Predict the quality score of a rear projection television, which cost about $5,000. Is that within the scope of my available data? Well, the other TVs that were in the sample all cost between what and what?
1,700 and 2,700
Or 1,500
or 15.
and 2,700. Nothing anywhere close to 5,000. So what's the answer to condition number 3? No. Even though the scatter plot didn't look like there was a linear correlation, and the R value confirmed that there's not a linear correlation, and our prediction is outside the scope of the data, will the calculator still give me a regression equation? Yes, it will. But will I use it? No, I won't. That's the most common mistake on the homework. Just always taking whatever they give you and plugging it into the regression equation without asking yourself, are the 3 conditions met? My regression equation, y hat, in the form a plus bx. Let's say it tells me to round a to 1 decimal place. That would be 48.2. If it tells me to round b to 3 decimal places, 0.008. Don't forget your x. So then do I just take the 5,000 and put it in place of x? No. Because of this no, and that no, and that no. If I know that I shouldn't use the regression equation, what should I use? The mean of the y values. You can either use this calculator sequence that I gave you on page 129. Actually, since I'm already more familiar, I already have 1var stats memorized. I can say stat calc 1var stats, but I have to remember I want the mean of my y's, not the mean of my x's. So make sure for list you have list 2. And I guess this could be a little bit confusing because it says X bar equals 66, but list 2 is my Y's. So that is the mean of my Y's. The mean of my Y's is 66. If we use that other sequence that I typed for you, if we had gone second and stat right above my stat key, it says list. If I curse over to math and then tell the calculator I want the mean, number 3, and then say mean of test or mean of list 2, that should give me the same thing, 66. I think I'll stick with 1 variable stats since I already know that. Just make sure you're finding the mean of list 2, not the mean of list 1. It's weird to me that, they give an answer there. 66 is the best prediction we can make, when we already know it's probably not a very good prediction. It's the best we can make, but it's not very good. All right, remember, I always think of Smokey Bear here. Only you can prevent forest fires. Only you can prevent using the regression equation all the time. You can only use it when the 3 conditions are met. Otherwise, you have to use the mean of the sample wise. All right. Yes, okay. That's the only 2 examples I have. I forgot we're supposed to talk about 7.4, and we can do this real quickly. It's just about causality. We know everything we need to know about correlation, but because there's correlation, can we automatically say, so X is causing Y? No, we can't. Correlation may suggest causality, but by itself, correlation never establishes or proves causality. Much more evidence is required to suggest that one, or to establish that one factor causes another. Earlier in 7.2, we found that correlation between 2 variables could just be a coincidence, or both things could have some underlying cause, or yes, one variable may actually be causing the change in the other. The process of establishing causality is essentially a process of ruling out the first 2 things. You have to establish that, hey, this is not just a coincidence, and that's hard to do. And you have to establish that there's not something else causing both things to change. That's also very hard to do. Those 2 things are hard to control for in the experiments. We can rule out coincidence by repeating the experiment many times or using a large number of subjects. Because coincidences occur randomly, the same coincidence wouldn't occur randomly if you did the experiment a bazillion times. So not so hard to rule out coincidence. We can rule out a common underlying cause by controlling and randomizing the experiment to eliminate the effects of the confounding variables. If the controls rule out the confounding variables, any remaining effects must be caused by the variables of interest. See if I can make up an example real quick. If you wanted to know whether a person's, let's say a woman's heart attack risk was caused by her cholesterol number, then you couldn't just run the experiment, run the test. That would be an observational study. You couldn't just observe women over 60, because the same thing may not be true for women over 30 as is true for women over 60. You're trying to rule out age as a confounding variable in that case. Unfortunately, these ideas are difficult to put into practice. To rule out coincidence could be very time-consuming and expensive. To rule out a common underlying cause, the experiment must control for everything but the variable of interest. That's what's really hard to do. Moreover, there are many cases in which experiments are impractical or unethical, so we can only gather observational studies. You can't determine whether there's a correlation between cholesterol and level and heart attack risk by denying the control group cholesterol medicine. That would be unethical. Because observational studies cannot definitively establish causality, we must find other ways to try to establish causality. If you suspect that a particular value, the explanatory variable, is causing some effect, look for situations in which the effect is correlated with the suspected cause, even when other varies factor. Among groups that differ in only the presence or absence of the suspected cause, check that the effect is similarly present or absent. Narrow down, eliminate as many confounding variables as you can, and see if the results are the same without those confounding variables. Look for evidence that larger amounts of Look for evidence that larger amounts of the suspected cause produce larger amounts or smaller amounts of the effect. If the effect may be produced by other potential causes, make sure the effect still remains after these potential causes are accounted for. If possible, to test the suspected cause with an experiment. If the experiment cannot be performed with humans for ethical reasons, and you don't want to use lab rats, then try to come up with a computer simulation. Try to determine the physical mechanism by which the suspected cause produces the effect. If you can show why the mechanism that causes your cholesterol level to increase your heart attack risk, then you can say definitively there is a causal effect there. Sorry, this is just a bunch of typing. I'm going to skip some of it. It was difficult to prove that airbags, that children shouldn't sit in the front seat of the car, but if the car has airbags, because the deployment of the airbag is enough to crush a little skull. Obviously, you can't do an experiment and let some little skulls be crushed and some not. It's a horrible thing. So you could use crash dummies. You could use a computer simulation. Ultimately, when the experiments yielded a physical mechanism, here's exactly how the airbag is crushing skulls, then we can say for sure kids don't need to be in the front seat of a car with airbags. Sometimes correlation or the lack of a correlation can hide underlying causality. Let's get down to this example. During much of the first 2 years of the COVID pandemic, the U.S. Centers for Disease Control and Prevention strongly recommended mask wearing by people in public places. Nevertheless, some people questioned whether the masks were actually effective. In other words, they questioned whether the mask could really prevent the spread of the disease. This makes the question one of causality, because a claim that masks prevent, oh, that's supposed to be masks. The claim that masks prevent the spread is a claim that they cause a lower amount of the spread. Each dot on the scatter plot represents one of the 50 states or the District of Columbia. The horizontal axis shows the percent of the public that reported wearing masks. Now, do you automatically see a problem with this survey? Asking people, let's say it's a phone survey and you call and say, are you wearing masks whenever you go out in public? Is there a potential problem there? There's going to be some lying. I think we better observe. I don't know how we would do that, but yeah, there's a potential if this is just a self-reported survey. The vertical axis shows the case rate for new COVID infections. The data represents 1 week in October 2020, which was before vaccines became available. So, briefly describe the type of correlation the figure shows and the strength of the correlation. What would you say about the correlation?
It's like a weak negative correlation.
Definitely going downhill. So the higher percent of people wearing masks, the lower the number of new COVID cases. And And I guess if you threw out those few outliers, I'd say that's a pretty strong correlation. But maybe with these outliers, that certainly does diminish the correlation. Notice that Wyoming doesn't fit the trend well. Can you think of a reason why Wyoming might not be expected to fit the trend? Here's Wyoming right here. Only maybe 58% of people were wearing masks when they were in public, but yet they had a comparatively low number of new cases.
Swelling population.
And it's not really the size of the population, it's the spread of the population. It's population density. People per square mile in Wyoming is probably one of the lowest in the US. And so it would matter less if you wore a mask in public if people were so spread out just because of the population density. I tell you what, we are out of time. Would you, because it may help you in the homework, will you read this C part before you start the homework? And that's how we'll start Wednesday. Wednesday, I'm going to check your answer to these 3 things right here. We'll make sure we agree on those. And what's due on paper Wednesday? Chapter 7 review. All righty. See ya.